So we really wanted to begin our discussion of acids and bases with the classic acid-base definition that we were exposed to in general chemistry. And that, of course, is the Bronsted-Lowry definition. Bronsted-Lowry essentially is the intermediate definition and states that a proton donor, and when we speak of a proton donor, we're really looking at a hydrogen atom that has been ionized by losing an electron. This is a Bronsted-Lowry acid. While a proton acceptor which is generally thought to be a lone pair of electrons, best exemplifies a base. And so from the Arrhenius definition, it is the definition of a base that is expanded upon. And so while ammonia would not be considered to be an Arrhenius base, it is a prototypical Bronsted-Lowry base. So let's look at a common example of a Bronsted-Lowry acid-base reaction. So we're going to consider hydrochloric acid reacting with ammonia. And of course, we're going to continue our little foray into arrow pushing mechanisms. And so the base and its lone pair of electrons makes a bond with or abstracts a hydrogen. Since hydrogen typically does not make two bonds, it releases its lone pair heterolytically to the chloride ion, and we obtain the ammonium ion. Of course, this is aqueous, and the chloride anion, which is also aqueous. Of course, HCl is aqueous. Ammonia is in the liquid state. When you have two species that differ by only one proton, they're called acid-base conjugates. So this would be a base and a conjugate acid. Notice the conjugate acid is more positive than its parent base. In other words, I go from neutral to +1. Also, hydrochloric acid and Cl- also differ by one proton. So this would be the acid, while Cl- is the conjugate base. Notice that the conjugate base is more negative. So we go from neutral to negatively charged. So let's look at a more specific example, and I'm on slide 3.3 right now. We have T-butoxide. And water. We use just a little bit of common sense. It makes most sense that the negatively charged ion acts as the base. And so again, the tail of the arrow is where the electrons are. Tip of the arrow is where the electron goes. Bond breaks so that the electrons go to the more electronegative atom. And our products will be T-butanol and OH minus. Now usually we can look at the favorability of a reaction by measuring a lot of different mathematical parameters. For example, pH works. Ka, or the equilibrium constant for acid dissociation, works. We can also use pKa. So the smaller the pKa, the more acidic the parent acid. Water has a pKa of 15.74, while T-butanol has a pKa of 18. And we can estimate our Ka as 10 to the minus pKa of products minus the pKa of reactants. So our Ka is 10 to the 18 minus 15.74. So our Ka is estimated to be 10 to the 2.26, which is going to be greater than 1. And so this is a product favored process. Now we can take this a step further and simply look at answering some acid-based questions now in terms of structure. For example, if I have dimethylamine, and I react this with H2O. Of course, you want to take the time and make sure you've got your Lewis structures correct. The amine is going to be a better base than it is an acid. And so we will have proton transfer. That's an acid-base reaction. And of course, we'll have dimethylammonium. Plus, we will have OH minus. Now, again, knowing pKa's really helps us predict, so we know that the pKa of acid and reactants is about 15.74, and the pKa of a protonated amine is between 9 and 10. Let's take the more conservative point of view. That means that the Ka of this reaction for the forward reaction is equal to 10 to the minus 5.74, significantly less than 1, and so this is reactant favored. In other words, if I tried to do this in the lab for about every 30,000 molecules that I actually check that. For about every 300,000 molecules that I have, about one of them would actually make the product of interest. So this would not work to my advantage very well in the laboratory. So I'd want to use a stronger base than dimethylamine. Again, if you look at the curved arrow methodology, tail of the arrow always begins with the source of the electrons to the electrophile. So we push the electrons from the lone pair of the nucleophile to the empty, lowest unoccupied molecular orbital, LUMO, antibonding orbital of the electrophile. Bond breaks, goes to the most electronegative atom, and then you have to essentially investigate and estimate the magnitude of the Ka constant. If it's greater than 1, it's product favored. If it's less than 1, it is reactant favored. This is really our first foray into mechanism drawing, and it will be one of the more important skills that we'll keep with us throughout the course. Let's look at another example. Of course, I'm getting this one from slide 3.6. And in this example, we have hydroxide ion, and we have acetic acid, active ingredient in vinegar. And so the base attacks the acid. And when I say it attacks the acid, the lone pair on one of the most nucleophilic atoms is going to form a bond with the electrophilic hydrogen ion, and then both of the electrons shared with the oxygen will go to oxygen to produce acetate. So my byproducts will be water plus acetate. Now again, we can do a pKa analysis to begin to make a prediction about the favorability of this reaction. Acetic acid has a pKa of 4.74. Water has a pKa of 15.74. That means the Ka will be 10 to the 11. That means for every 100 billion acetic acid molecules that I have, after equilibrium, only one will remain undissociated, while the other 99,999,999,999 molecules will be dissociated. So here, the products are greatly favored. So this step is called a proton transfer step. And in class, we'll actually explore some different ways that we will observe proton transfer steps in our analysis of acid-base reactions. So one thing I'd like for you to think about as we prepare for class tomorrow, strong acids have high Ka values, low pKa values, low pH values. You should be able to explain all of those trends using principles of structure and bonding. you should be able to explain all of those trends. Let's take just a few moments now and look at some important pKa values for functional groups that I will expect you to know. And so what we're going to do is I'm going to list a number of functional groups and then write the pKa of the most acidic proton, and the ones that I write on this screen are ones that I expect you to know. A protonated carbonyl, as in a ketone, has a pKa of negative 7.3. HCl, pKa of negative 7. Hydronium, pKa of negative 1.74. Sometimes that's as great as negative 1, but negative 1.7 is a pretty good characteristic of thumb to use for pKa. Any kind of carboxylic acid will have a pKa ranging from 3 in an amino acid to 5 when I have long alkyl carboxylic acids. If I have a diketone, such that I have a couple of hydrogens that can be removed and result in a lot of resonance stabilization, that pKa is around 9. If I look at phenol, which is an alcohol where the OH is attached to a benzene ring, that pKa is about 10. Water has a pKa of 15.74. Absolutely need to know water. Most alcohols will have a pKa of anywhere between 16 to 18. Any ketone, pKa is around 19.2. Any aldehyde, pKa is about 17. Continuing on, an alkane, pKa values between 50 and 60. They're universally thought to be the weakest, among the weakest acids that exist in nature. If I have a vinyl alkene, pKa is about 44. But if I have an alkynyl hydrogen, that pKa is about 25. If I look at an ester, pKa is also 25. If I look at a nitrile, such as acetonitrile, that pKa is also about 25. If I look at toluene or methylbenzene, that pKa is about 38. If I look at ammonia, pKa is also about 38. So what I would do is I would just recommend that you learn all of the ones I've placed in here. Using note cards is a great way of doing that. And in this way, you'll be able to estimate pKa's and to predict whether a reaction is going to be reactant favored or product favored. And I'd like to do one final example, and that's where I'll stop today's podcast. So let's look at the following example. If I have a carbanion and I have a water molecule, and the proposed mechanism is proton abstraction to give me the alkane plus OH minus. The acid in reactants is water, it's 15.7. The acid in products is butane, its pKa is 50. That means the Ka is on the magnitude of 10 to the 34.3. Much, much greater than 1. That is product favored. It's kind of like killing a cockroach with a laser-sighted AR-15 semi-automatic, but it gets the job done, ladies and gentlemen. So this is so great, this reaction really wouldn't be considered to be at equilibrium. So this concludes what I want to cover on our brief review of acid-base chemistry in terms of mathematical parameters. Next podcast we'll look at a qualitative acidity assessment. So we will simply look at a molecule structure and look at its relative acidity as compared to other acids. And then we can use our pKa values to validate or invalidate our hypotheses.